I'm excited to be here. I would like to turn the focus now to quantum sensing from an aerospace end user perspective. We have quite a portfolio, a growing portfolio also at Airbus, working on this super exciting topic. And I've chosen to present to you one example how we make quantum sensors ready for our products, for our environments. And I've chosen a tough one, namely how we make them ready to go into space. So before I start, I would like to give you first a little bit of context about Airbus. You probably know us best for our commercial aircraft. Maybe some of you have even taken an Airbus to come to this place. So what you see here in the middle, this is one of our A320 aircraft. This is our most important product. We have sold more than 10,000 of those aircraft and delivered to customers. And about every 2 to 3 seconds, somewhere in the world, this aircraft is taking off. But Airbus is more than that. We are also offering defense products. You see some of them here on the left side. We are producing helicopters. We're actually the largest helicopter manufacturer in the world for civil helicopters. And what you cannot see in this picture is our space segment. And this is also a very important business line of Airbus. So we are Europe's largest satellite manufacturer. We are active all along the space value chain, so from the launch-related services, then of course satellites, up to applications and services. So we are building various kinds of satellites, telecom, Earth observation. We're active in human spaceflight and also in space exploration. So overall, you can say this is covers a broad or a big part of the overall aerospace domain in terms of products and also in terms of services. And there's one thing those products have in common. They are all filled with sensors. So an aircraft is filled with sensors, a helicopter, a satellite for sure. And we already know there will be much more sensors in the future in all of our products. So that's why we are naturally interested in quantum sensing. And there are two properties, how you can categorize those sensors. The first one is they have a very high sensitivity, since coming from the measurement principle. But it turns out this is not the key advantage for many of our applications. Another advantage of quantum sensors is that they have intrinsically a very low drift. So why is a drift a problem for us? So if you have a drift, this means you need to calibrate, you need to recalibrate. This reduces your efficiency. This can produce additional costs and also can decrease the overall capabilities. So these properties is why there are so many applications in the aerospace domain. Can we go to the next slide, please? And so I'm in the lucky position that I'm the last speaker, so we have already heard about many of them. But I would like to highlight again that navigation is, of course, at the very heart of the aerospace sector, so we can improve navigation. We just have heard about RF receivers. We can think about testing capabilities, timing improvement, improved radar and LiDAR capabilities. And specifically at Airbus, we have one focus area to use quantum sensors to improve our Earth observation capabilities. And there are actually various things you can do to improve those satellites. And I choose today one example where we take those quantum sensors to improve our capabilities to measure gravity. So maybe that's a bit surprising for some of you because typically, Earth observation, people think about spectrometers. So we are building, for example, for the European Space Agencies, various spectrometers who can measure the pollution in the atmosphere, can measure greenhouse gases or other parts of the atmosphere. You may think of imagers, like visible or thermal imagers, for example, very interesting and very important for weather predictions. But there are actually a lot of processes which don't have signatures if you just use those types of instruments. They have their signatures in the gravity. For example, surface properties like ice melting, like sea level changes, circulations, and even more prominent interior Earth processes. So volcano activities, raw material reservoirs, groundwater reservoirs. So there's actually really a lot depending to have those data. And this is why we already have, since decades, operational systems in orbit who measure the gravity. And Airbus is, can we go to the next slide, please? So Airbus is actually very active in this field. It's very at the very core of our portfolio as well. So you see some of those missions here which measure the gravity. For example, the GRACE mission, which is measuring the gravitational field. There are also missions which measure the gradient of the gravity field. And there are two main things typically what are required. First, you need an operational continuity. So that's why you have always follow-on missions. And of course, scientists and the end users are asking for higher precision. And here quantum comes into the game. So let's first have a look what these data look like. And can we please go to the next slide? So this is here taken from NASA. It shows you the gravity anomalies which are measured. And to measure this with a satellite is the only way to get a global measurement. So basically, we have satellites in orbit who measure on a monthly basis this type of gravity signatures and also all the related changes. So what is this useful for? There's actually a lot of applications you can think of. And if we go to the next slide, I have here an example. If you can start the video, please. We can see here from the GRACE mission the observation of the ice changes in Greenland. So there should be a video now. Oh, sorry. Is it possible to start this? Okay, then sorry for that. So normally you should see here the decrease in ice over time. So you see there it goes. So you see here the mass losses. You see each year the seasons in these small oscillations and the overall ice loss, and which accumulates over 15 years to about 4,000 gigatons. So this is actually maybe showing you an example how powerful these gravitational measurements are. So now I would like to give you like a little bit of insight how this works, because we don't need quantum to do that. This is already operational. So this is one of the methods which is used. There are several of them. It's called satellite-to-satellite tracking. So you put a formation of two nearly identical satellites into orbit. They are flying typically in a low orbit about 500 kilometers. They have a distance of about 200 kilometers. And they're connected with a microwave or an optical link, so they can measure the distances to a very high degree, so typically on the order of micrometer. So how does this now work? We go to the next slide. You can see here what happens if there's a gravity anomaly. So first the two satellites arrive, then the first one gets a gravitational pull, is accelerated, so the distance between the satellite increases. Then we go further. The second satellite is also passing, gets a gravitational pull, and once both of them they have passed the anomaly, they are again the same distance. So basically what we do is we are translating gravitational signatures into distances between the satellites, and if we measure them, we can derive the gravitational field of the Earth. So that's exciting. So why do we need quantum? Right? Because it works. This is, of course, a bit idealized. It's not so easy because there are many instruments on board of those satellites. For example, you need star tracker to have a good understanding of the orientation. And also, you need GPS to get the right position. And you need a very high-performant accelerometer to be able to distinguish the gravitational pull from other gravitational effects like drags due to atmospheric effects or sun pressure, etc. And those accelerometers are really very high performant. And if you go on the next slide, and here you can see this, typically one uses electrostatic high performance accelerometers. They operate at a range of 10 to the minus 10 to the minus 12 meter per square hertz per square second per root hertz. And they're actually very good. The problem is they are exposed to drifts. So if you remember, every classical sensor is exposed to drift, and in particular, if you put them in space, there's thermal stress, there's space radiation, which leads to discharges. So if you look at the long time scale, we always get an error increase. And this is what you see here. So if you go to very low frequencies in the millihertz or even lower range, then the acceleration noise goes up. And this is a big limitation. So now if you right remember, the quantum sensors, what I was saying in the beginning, they are intrinsically low drift. And indeed, if you add here a quantum sensor, if you can go to the next slide, please. We use, for example, atom interferometry, then we can get a flat noise spectrum even for very long times. So I am in the happy position that I will not go now into the detail of atom interferometry because Michael was already mentioning this. But what I would like to tell you is that this technology is really changing the performance of the overall mission. And if you go to the next slide, then you can see this. This is a work which has been done in the last year to calculate the differences in errors from such a gravity mission using, on the left side, a state-of-the-art high-performance electrostatic accelerometer, and on the right side, a quantum-enhanced version. And you can clearly see that there's a big difference overall. The level of errors reduced. But there's another big difference. You have this kind of aliasing structure, which is coming from the measurement modes and the different orbits of such a system, which are nearly completely vanishing if you have a quantum sensor on board of this satellite. So that's great. So, but it's obviously not very easy. If you go on the next slide, you can see for those ultra-cold atom systems, how much has happened over the last 30 years. So the first sample of ultra-cold atoms was in the beginning of the 90s, quickly awarded with the Nobel Prize. And then scientists realized very quickly it's interesting to work with those ultra-cold atoms in zero gravity. So here I'm showing you some of the initiatives. This is of course not comprehensive, but there are initiatives from the German Space Agency to do drop tower experiments where you could already have like maybe 10 seconds of zero gravity. For the French Space Agency was working on zero-G flights, so where you had even a longer time than in zero-G environment. There was a very nice experiment also done by DLR where they were able to include this technology into a sounding rocket and let it fly on above 100 kilometers and had already a quite long zero gravity time. And currently there are also efforts ongoing between NASA and also the German Space Agency to bring this technology on the ISS. So the next logical step, and this is what we need for a gravity mission, is to bring this technology into space, into an orbit. And this is what the so-called Carioca project is about. The objective of this project is to realize a quantum space gravimeter pathfinder mission. And this is a European project, and here Airbus is, if we go to the next slide, is heavily involved. So the challenge is to transition this technology, what you have just seen, to an operational space instrument. And this is not easy, right? Because what you have to do, you have to design it in a way that it survives all the stress around launch. You have to design it in a way that it can operate in the space environment, like the thermal environment, but it can also survive the space radiation, etc. And it has to be completely autonomous. So there's no way, if there's any mistake, there's nothing you can do to fix it anymore. So that's why there's a lot of maturation steps now necessary. And in this project, we are building in so-called engineering model. This means in the space language that you increase the TRL to TRL5. We are testing the critical technologies, and we are preparing also the industrialization. And this is not done by Airbus itself. You see there's a large consortium involved with the German and French Space Agency, with a lot of academic partners and also industrial partners, aiming to develop this instrument for the Quantum Pathfinder mission. And for those experts here in the room, it's going to be an in-orbit, a long-track atom interferometer accelerometer. So this is the Carioca project, covers the instrument. Airbus is leading here the instrument development, and we are also in charge of the integration and the physics package. And the physics package is the heart of the sensor, so the vacuum system where all the atom chip is located, and basically the heart of the full instrument. The next step is then you have to create a mission, and this is now the roadmap. If you go on the next slide. So we are currently, we have been working in the last years on this instrument part. On the upper side, you see the QSK Pathfinder mission development now. So we have just recently started now with the phase A to define the mission, so define the satellite, the platform, etc. This will now run through the different phases, implementation phases, and the objective is to have a quantum space gravimeter Pathfinder mission in orbit by the end of this decade. So what will this mean? This means we have, for the first time, a quantum accelerometer in orbit. We can prove that it works. We can prove that it works in this environment, that it's operational. And once we have proven this, it will allow us to define and to build the next generation of quantum gravimetry mission, where we have the full capability, what was I showing to you in the beginning, where you see all these advantages. You get gravity data with an unprecedented accuracy. So this is, I think, a very exciting project, but it's also a very challenging project. So not all of our projects are so challenging. There's many things you can do in aerospace where you can maybe just bring a quantum sensor into air. And we have already heard a lot about navigation in this conference. And can we please go to the next slide? Because it's really exciting to see the progress in the field, how the engagement is increasing. And I would like to use this opportunity also to promote a collaboration we just recently made public. So Airbus has here locally, very close actually to this conference center, an innovation center, and this is called A-Cubed. A-Cubed has the objective to leverage the talents, to leverage the startups, to leverage all the technology which is available here in this ecosystem for aerospace. And we are collaborating with Sandbox A-Cubed for navigation. So here we are going into the air. And we are working here on what is called magnetic anomaly-aided navigation. So Michael talked about this, where you basically use magnetic field anomalies, which are very difficult or impossible to jam or to spoof, to correct for drifts in your navigation system. And we are doing here, you see, we have done already in the last year a couple of flights. We have collected a lot of data now to understand the performance of those of the system. I think Jay was mentioning this this morning in his session, that these systems are extremely interesting, but they are only providing a building block to the overall navigation system. And this is something we need to test. We need to understand how to set up the overall system and how to integrate this technology into our overall navigation system in the future. So this was a kind of an outlook. I would like now to go to the last slide, please. And just to summarize that, I hope I could convince you that quantum sensing matters for aerospace. It will change aerospace, it will change aviation, it will change space. And we are really excited to be part of this journey, and also excited to work with so many of you, and hope it will continue to be so exciting. Thank you very much for your attention.